Yeah, so we're gonna look at the scenario where you make Boolean circuits that are analogs to multi-layer perceptrons, and then you figure out the representation. We're trying to figure out the representational capacity of these models. So like you have like these input variables, and we're restricting them to be Boolean. And then you have the first hidden layer, and we're also like restricting that to be like size in. And then we have a single output at the next layer. And the thing that happens is that every unit is computing a linear threshold function, which means it can be written as sine IGN wx plus b, right? Like just like a real neural net. Although like people use like ReLUs these days, which I don't really know the difference between like a ReLU and like a sine IGN function, but yeah, so like if you just have a single hidden layer and a single output, like what are all the functions that can be computed? And but we're actually constraining even more, because it's hard to understand. The the overall description of what's happening, like when you pass in an input, is like the hidden layers update. So the hidden layers become like a binary string, 1010 whatever, and then to compute the output, you're taking the hidden layer binary string as an integer, and then you're indexing into the output unit to determine the output. And that is the same as if you were just computing the like wx plus b operation. And right, so we're looking at those models, except we're also constraining the b's to be 0, no bias. It's kind of like in subsequent videos as possible. We'll, it's like we're gonna be like, oh, what is if you add in bias? How does that increase computational or representational capacity? So anyway, we have 0 bias, and then we have the W's are like sorted, and they're positive. And this is what happens on the screen if you are in 4 dimensions and you're asking what are all the functions that can be represented as sine IGN of wx plus b, where b is 0 and w is all the elements are sorted and positive. And it turns out there's only 3 things that can happen, and they are kind of interpretable. So I guess we'll try. We'll do like the interpretation, and then but then yeah, then we're going to try to like come up with an explanation for, because we did like a previous stream where if you randomly sample circuits slash MLPs, multi-layer perceptrons, if you randomly sample circuits with these with random parameter functions, like one of these functions being assigned to each unit, it turns out like every single function like is one of these functions, and yeah. So we're going to try to see if we could come up with an explanation for that, and like in particular, like is that just like an artifact of like sampling? Like it's very hard, it's probabilistically unlikely to produce a new function. Is it an artifact of like low dimension? Because when we were doing sampling, you really can't get much more than like n equals 10 or something. You guys like lawnmowers, isn't it? Hell yeah. Yeah. Okay. So anyway, these are these are Boolean functions and 4 inputs, right? So there's like the rows are the inputs, and they are sorted first by Hamming weight, and then by lexical. So they're not exactly in like standard. They're not in like lexical order. They're Hamming weight first. And right. So I mean like, and so these are all functions that can be written with sign wx plus b, where b is 0 and w is sorted. Right, and so I mean like, yeah, I mean like, right, so like the purple indicates like a negative output. Yeah, I mean it's literally, because the bias is 0, it's literally indicating that the dot product of this with whatever the weight vector was is negative. And however, a 0 here means -1. And so like, the weight vector is always all positive, so therefore that dot product is always going to be 0. If you have 0, 0, 0, 0, it's always going to be negative. Anyways, it's like the first column, is just saying that like the magnitude of the largest weight, the leftmost weight, is larger than the sum of all of the other weights. So like it controls. So like it's a 1 here, so it's yellow. It's 0 everywhere else. Yada yada. And then the next column is saying like, this is not true, but the sum of the middle 2 weights is larger than the sum of the outside weights, which yeah, so saying like whenever the middle 2 weights agree with each other, they control, and when they don't agree, it's I mean in this case it's already predetermined, like all of these rows are predetermined. Then the third column is the I guess the third column is saying that the outer two weights sum is larger than the other two weights, so they control. Great. So anyway, let's what is with the lawn mowing? Jesus. Anyway, so anyway, what we want to do is we want to look at like a circuit that has like 3 units, one output, like a hidden layer with 3 units, actually 4 units, and one output unit, and we're assigning these 3 functions to the 5 total units. There's 3 power 5 possible circuits. That's cool. And I think, but anyway, yeah, like we know empirically that the setup, you cannot produce like a novel function, like a function not in the starting set. And so we're trying to figure out why. I mean, it's kind of like if you just consider like this function by itself, which is the input identity, it's kind of easy to see that it can only ever produce itself, because it's just selecting a unit in the previous layer and like copying it over. And so it just does that for every layer. If every unit is like majority, it can only ever produce majority. Yeah, I guess you could try to reason about, okay, like, what if I allow the 2 circuits? And but anyway, we had the idea for an argument in the following way, because it's like if you focus on a single row, single input, lawnmowers are crazy. If you focus on a single input, you have, as like the programmer of the circuit, you have like complete freedom as to where this one input is being mapped, assuming it has both a yellow and a purple column in that row, right? I mean, like these rows, you don't have any freedom, because any selection of these columns for the hidden layer, they're always going to be purple. So these inputs will always be mapped to 0, 0. Which means they will always get purple as output, because for any possible selection of the output units, 0, 0 always is mapped to 0. Right? Yeah, so like you really only have also there's like mirror symmetry because of the bias being 0. So you really only have like 2 rows in play here. And I mean, again, like specifically we're trying to produce any function that is not one of these functions. So, you know, so for already, like, the rows that are constant, there's no way that, like, you could produce a function that has a yellow at one of these rows. Because any hidden layer will map these rows to all zeros, and any output unit maps all zeros to 0. So I guess you're really more asking for, like, the 2 rows in play. You know, I guess you're asking, like, well, I mean, the only thing that's not happening is yellow, is, like, them both being yellow. Yeah, yeah, that's the only thing that could happen. Right. Right, okay, yeah. So, right, okay, so I guess we could ask, right, I mean, yeah, like, the only function that is not one of these functions that we could possibly compute is where both of these rows are yellow, or both of those inputs are yellow. And, right. So, right. Okay. So, yeah. Right. Okay, so what we need is, like, a mapping that, you know, is going to map this input into a yellow, and also this input into a yellow, right? Like, simultaneously, right? Like, you can't do it just as sine wx plus b, but, you know, we're not, you know, we're doing, like, a circuit with a hidden layer. So, actually, I guess you could, I mean, you could do that algebraically. You could, you know, and you're like, wait, well, yeah, I don't know, I mean, that'd get hairy. So I think that's what we're asking, though. We're saying, like, okay, I want to map this row into a yellow, and this row into a yellow. Yeah. So I mean, for instance, you could say, like, okay, I'm going to map this guy to itself. You know, so I'm going to pick, like, so the columns, you know, I'm going to, like, 1, 0, you know, and 3 zeros, right? Like, I mean, you can repeat a column, so you might say, like, I'm just going to map this guy to itself. I think we can actually, let's just do that. We can do that. We have a little cell that will do that. Programmatically, so we don't have to try to figure out what it would look like. Okay, so we want to map this guy to itself, so we're going to pick columns 0. Note that that selection is determined, because there's only 1, 1. You know, so, and we have to pick, like, 4 columns, so we'll pick, like, 0, 1, 2, 2, right? Good. It's similar to what I already have in there, but 0, 1, 2, 2. Oh, right, I gotta run another cell. Gonna run that cell. Okay, that should work. Okay, let's look at this. Okay, so this is the hidden layer we just specified. Right. And we want both of these guys to be mapped to a yellow. Let me close that. Oh. Yeah, I wish, they won't give me GPT. But anyway, the, right, so the situation is that this guy, okay, he mapped to himself. Well, I mean, if we want him to be yellow, then as the output unit, we would have to select that column, which would enforce this column being purple. Okay. So, let's try a different strategy. Well, I mean, any... I mean, it seems like there should be an easy, Anyway, okay, what if we just try to map this guy to, say, down here? So we're gonna do this guy, we're gonna choose, yes, so we want it to be 1010, so it's gonna be 01, say 01. And, right. So, so this guy is now mapping to 1010, which if we go to our outputs, is always yellow. But the other guy is mapping to the inverse of that, which is always purple. So... I mean, it feels like there's some sort of, thing that's happening. Well, okay, yeah, let me talk about the other because what we were looking at here was very specific to n equals 4. Yeah, the more general idea was something again, you can pick a specific row and determine what binary string you're going to map it to. And usually, so that binary, the new assignment, is either going to be greater or less than the than the row itself. Yeah, and so then there's some argument that's not clear, but it's if you're mapping one, if I'm mapping this to a greater string, meaning I'm adding a 1 to it, then that in some sense, like, you have to be maintaining the order of what's already happening, so therefore you can't produce a new function. It's kind of the argument we're going for, and it doesn't, it's too, you know, right, yeah, I mean, it's something like, if you're putting a 1 in this row, you're necessarily putting 1s, or I guess in this case 0s, in these rows. Well, I mean, like, yeah,